Hello and welcome to FEM Expert. Today we will present you another basic tutorial in which we will generate a plate with volume type elements in Ansys. To begin with, as usual, we'll start with Ansys interface. For this tutorial we will first generate a key point of a plate, then we will extrude that plate and generate a volume, and upon having that volume we will proceed to the normal analysis in order to have that plate simulated with volume type elements. Therefore, the first thing to do is go to preprocessors, modeling, create, and key points. We're going to create 4 key points in the active CS, which means the active coordinate systems, which is in this case is the 0, which means the coordinate system that you can actually see on the screen. So we're going to generate a series of key points in the XZ plane. So for the first one, we're going to generate a key point on the 0, 0, 0 coordinate. For the second key point, we're going to generate it on X on 1 meter. We're going to apply. The third point is going to be at the same X 1 meter but at 1 meter on Z. Apply. And for the fourth point, we're going to have the X equal to 0, and we're going to hit OK. We have the 4 points created. You can actually visualize them if you go to isometric view. And as I said, we have the 4 points, and now we're going to create an area or plate on those key points. So for that, we go to create areas, arbitrary throughout key points, and you have to select the key points in an established order. You can actually see while you're selecting the key points how is the area being made up. So we're going to go clockwise. You have to go either clockwise or anti-clockwise, but it has to be always in that order. We have the first, the second, the third point, and the 4 key point. We hit OK, and we'll see our plate. If you move the scroll of the mouse, you'll see that you zoom in, zoom out, but that you lose the visualization of the plate because you only have the key points. In order to visualize the plate, you can go to plot and plot areas, but then you lose the key points, or you can do this little trick, which we recommend a lot, is typing on the bar gplot. You can just gplot or gplot, it doesn't matter, which means global plotting, and here you can see all the entities that you have, which are areas, lines, and key points. If you zoom into at some place, you'll be able to see that you see the key point and the 2 lines and the shell. To go back, you can go to the zoom back model, and now we have at this moment we have the lines, the areas, and the key points. But we want to extrude that area, so in order to perform the extrusion, we're going to copy one of these key points up onto the y-axis at 3 millimeters, and then we're going to extrude this area 3 millimeters up to obtain the volume. So for that, the first step is to go and copy a key point. We're going to copy this key point, the key point number 1. We're going to hit OK, and we're going to copy it at 3 millimeters from on the y direction. We divided by 1,000 because we're working on a meter system. After we've done that, you'll see that you have the key points. If you actually zoom in, you'll see there's 2 key points, the key point 1, which is exactly here, and the key point 5, which is a little bit higher. We'll go back to the fit view, and we're going to create a line between those 2 key points, straight line. Here you can see the first point that says the key point number 1 has been selected, and very closely to it you can select the key point number 5, which is the second one. We hit OK. If you're not sure if you created the line right, you can always zoom the model. We're going to go to zoom. You can use also the scroll or the dynamic mode to move and zoom stuff. And we're going to plot again the gplot. And as you can see, we have the line created between those 2 points. So now we're going to scroll back actually we're gonna go to this fit view again, and we have to extrude this area through this line. So in order to do that, we're gonna go to operate, extrude areas along, you can do normals, axes, but we're going to do it along lines this time. So you select the area that you want to extrude, hit OK, and then you select the line. You can again use the zoom. Oops, I did it too much. You can do the zooming right now here, and you'll see the line has been selected. We have line number 5, and as soon as we hit OK, you'll see that the volume comes in. Actually, you can look one of these edges and you'll see that there's a thickness of it. To verify this, you can always go to plot volumes, and if there's anything, it means there are volumes, or if you're not sure, you can always list the volumes to be sure that you are actually looking at volumes. Once we have done that, well, one of the problems using the extrusion operation is that you will end up, like the way we did it, we will end up having doubled lines or doubled areas or double entities. And although it's not the situation in this case, because we're just going to mesh the volume elements, sometimes they can create problems. And it's always good to get used to work with clean models and in a professional way. So we're going to go here. I'm going to show you with zooming here, and if we plot the lines, I'm going to use dynamic mode, zoom in a lot until we see the line here. Well, it looks like there's only one line, but if you go to listed and we list the lines, well, if you go to list the lines, you'll have all the lines. So I'm going to cancel it, and I'm going to have here in the command bar the command ls line list, which is l list, that comes from line list, comma p from picking. Once you do that, you can list any lines that you want by clicking on them, and if we click here, it will tell us there's 2 lines at these locations. We picked up the line 5. If you go to next, there's line 7. So we know there's 2 lines. This creates a problem because anytime that you have 2 lines, there might be problems with meshing or problems with the model or connection. So what you need to do is merge those lines, convert those 2 lines into one. For that, we're going to go to numbering controls, and we're going to hit merge items. You can merge nodes if you have elements, or you can merge key points if you have any other entity that you want to merge. So once you hit OK, if you don't get any messages, it's good. And then if we list again if we do the line list, comma pick, and we go here, we'll see there's only one line and only one. So once we've done that, we're gonna go get to gplot, fit the view, and at this point we have our model. Now we have to start following the steps of finite element models. The first one is define the element type, add the delete. We're gonna go to add, and we're gonna choose solid, and we're gonna define the default one, the quad for node 182. Here, when you picked up this one, although it says it's a solid, for some reason you'll see that it's actually a plain type element. So we're gonna keep that in mind, and we're gonna keep following the steps, and then I'm gonna come back and change this element because this is not the one we want. But let's assume that situation happens to you. So we have defined the element types. Because we're working with volume type elements, there's no real constants or sections, because the geometry of the elements define these properties. So now we're going to go to material properties, material models, and we're going to define the models. We're going to do a structural linear elastic isotropic material. This is the Young's modulus. There's going to be a steel 2.1 e exponential 11 because we're working in the international system. And the Poisson coefficient is going to be 0.3. We hit OK. We have the linear isotropic properties, and we're also going to put density, which is going to be a steel's density 7,800 kilograms per cubic meter. I'm going to hit OK. Now we have the properties defined. as I say, we don't need sections, we don't need to do any more modeling. So the next step is to tell the program that these are the properties, that this volume has these properties. So we're gonna go to meshing and mesh attributes, picked volume. We're gonna pick this volume, we're gonna hit OK, and here we have our first problem. The type of element that we can assign is only plane 182. Our thing is not plane, so we're gonna go back to the add delete elements, add edit delete. We're gonna go to delete, and then we're gonna add again an element. And the one that we want to use is the brick 8 node 185. So solid brick 8 node 185. We're gonna hit OK, and we have it there. After we did a little change, we go again to the meshing, to the picked volumes, we select the volume, hit OK, and then we have the material number 1, real constants not necessary, solid 185, and we hit OK. Now the next step in any models is to proceed to get the meshing. For that we're going to use the mesh tool, and we're going to set a global size, which is for all of this. Since we have 3 millimeters in thickness, the best ratio would be obtained for 3 millimeters, but that will give us too many elements, so we're going to do a 10 millimeter meshing. So we're going to set the global. On the on size, we're going to put 10 divided by 1000 and hit OK. Now we're going to go to meshing. We're going to mesh with tetrahedrons. We're going to choose the default one with free and see what happens. The free, it already tells us this warning with the brick shapes. If we hit OK here, we ignore the mesh, the warning. It will give us another warning that says that tetrahedral meshes can be much less accurate than bricks, and it's advising you to use the 10 node tetrahedral if available. Well, we'll close this. We'll zoom in, and although I know this can create a lot of controversy, there's a lot of articles and a lot of people and a lot of mathematicians that have demonstrated that tetrahedral elements are not as accurate as hexahedral elements. So even though we have this meshing that seems to be fine, we're not going to use this meshing. We're going to go back to the model, go back. We're going to raise the hidden menu from this button, and we're going to clear this meshing. Select the volume, and we have cleared the volume. We're going to raise the model again, and we're going to perform a hexahedral mapped meshing. We're going to click mesh, hit OK, and then perform the meshing. Now if we zoom in, we'll see that these elements are much better, they look much better, and they're actually tetrahedral elements. They're still not the most perfect ones, but they're quite good. There's 3 times the difference between this size and the length of the elements are 3 times, so we're fine. We're going to back to fit view, and now we're going to continue applying the constraints and perform the simulation. The first thing we're going to do is zoom in a little bit with the dynamic mode, and we're going to proceed to loads, define loads, apply structural displacement on areas. We're going to select this little side area, like we're embedding the plate just on the side. I'm going to hit OK. All degrees of freedom, we're going to hit 0. I'm going to put OK. I'm going to raise again this menu, the meshing tool, and I'm going to close it. You can see here that there's a symbol for the embedment. If we hit plot areas, you actually see it. It's there because we restrain the displacement on those areas. To simplify the problem, I'm gonna just apply the weight of the plate on the y direction. Like if we have the plate embedded on one end and just its normal weight on the other. I'm gonna do this by applying inertia, gravity, and global. As we mentioned before, the gravity application the appliement of the gravity can be done inertially. That means that your value has to be positive in the direction of the desired direction. This means has to be 9.81 on the y direction. When we hit OK, you'll see that you have the arrow pointing up. It's good. There's not a mistake. Although the acceleration, the rotational acceleration, it's downwards. But we're talking about inertial acceleration, so it has to be the opposite way. Anyway, if you made a mistake and you have it the wrong way, you just go back to the global and define it with a minus before the number. So once we have that, we can go to solution, solve, and solve the current LS. We hit OK, and we wait until the solution is done. It will take a little bit longer, there's more elements. Now we have the solution is done. We're pretty happy about that. And the first thing we're going to look is general post-processing. We're going to read the results, last set, which is the only one that we have anyway. We're going to plot results, contour plot, nodal plot, and we're going to see the degrees of freedom of displacement vector summation. I'm going to show you a couple of things here. As you could see, I'm going to choose the dynamic view and I'm going to rotate and move the plate. As you can see, the highest displacements are on the free end of the plate, and the small displacements obviously are where the embedment takes place. I'm going to show you another thing. I'm going to show you this. We're going to see the deformed shape here on the undisplaced shape keys. We're going to see the deformed shape with the undeformed model. And for the scale factor, we're not going to use it auto calculator. We're going to use a user specified. Here with 3 by default, we're going to put like a 15 maybe. We're going to try it to see. And now we have, here you have how was the plate originally, how the plate originally looked, and how it actually has been deformed. We'll go here again. We'll see with undeformed edge, deformed shape with undeformed edges. This gives us just the edge. And again, you can see the initial model and you can understand it, which is, it kind of confirms that the simulation has been performed right, that where the embedment takes place, there's no displacement, but where at the free end of the plate, there is a significant displacement. Well, a significant taking into consideration the values and the units that we're working with. Now the next thing we're going to plot, it's nodal solutions. Again, I'm going to show you the stress, and I'm going to show you the von Mises stress. The von Mises stress, I'm going to take this off. I don't want this thing. I'm going to keep the auto calculated, the scale factor. And as you could see, well, we have the stresses. Obviously at the free end there's 0, and the concentration of tensions is located at very closely and at the embedment. You see there's a very high variation of the stresses from the embedment towards the end of the plate. The next thing we're going to do, which can be very useful, and we advise you to use it when you need it, is to perform a vector plot, a predefined, and here we're going to do a translational U, just OK. We're going to keep all the other options default. And what you will see here is vectors that tell you or show you how this plate has been deformed. You can actually see the shape of it. The magnitude is straight correlated to the amplitude and the dimensions of the plate, so it gives you a very significant image of what has been happening to this plate. Obviously you can choose a scale on this again, but right now we're just going to keep it on auto. Okay, so I gotta rotate a little bit more on the model, and now you know. I'm gonna close Ansys, quit no save. So now you know how you can simulate a plate using volume type elements, and also you have the general knowledge to be starting to use volume type elements in your simulations. We would like to thank you for your attention, and we hope you enjoyed this presentation. For more presentation, please follow us on our community and on the social networks.